Welcome back. Today we're doing some more messing around with Unity, and hopefully today we'll see how much a $150 phone is able to handle in terms of simulating nuclear particle physics. People who are watching this from 270 will notice that the physics aren't exactly accurate here. Guess you better improve on that, huh? I don't have time to look it up. But we'll get something. Going here. So the first checkpoint is on Thursday. I expect to see some meaningful progress on Thursday towards your app. So on Thursday, there's not going to be a lecture. Just meet up in Discord, sit in a channel either with your teammates or with anybody you want. Talk amongst yourselves or keep working on your project. And I'll come to each of you individually and you can show me what you got. So hopefully you've got quite a bit of progress by Thursday. And I don't have any specific questions from anybody yet, so I guess nobody's run into any serious roadblocks, but again, I'm always looking for your questions so we can go into whatever part of mobile dev you're most interested in. It's a very big field, very big indeed. Alright, when we last left off with the Tokamak, we were trying to get the particles to bounce when they struck the floor of the simulation. The particles that don't get rendered until they actually run. So we did that. They bounce, although obviously they all bounce together, which is quite goofy, isn't it? Whee! Whee! So the next order of business is going to be to add a little bit of initial force to every particle to give it some more randomness. And of course, when we start a particle simulation, every particle has some kind of initial force that they started with. They're never completely at rest. So let's go ahead and do that. The next thing that I thought of after I did this was that if the shell is actually simulating the magnet rather than simulating the bouncing off of something, then it's not enough for it to just reflect back. It has to add force every time you strike the shell. So we're going to have to figure out the force the particle has now and add to it by magnet magic. Because it's not enough to just deflect it. We have to deflect it with stronger force. We'll see if that's even possible as we go. Alright, the adding along the collision normal I already did. Last time, if you saw, I think I left off just before I wrote this line, so I might have written this line right at the end of class, but I'm just taking the first of the points of contact at which this particle struck that outer shell, and then I'm taking the normal along that, so that's the vector normal. I tried to draw it for you earlier, but, well, if you don't know what a normal is, it's not a math class, but it's a vector normal, and I multiplied that by the quantity of force that I want to issue. So I'm going to actually make a field for that. We'll call it public const float magnet strength 5,000. I'll change that as we go. Alright, so for the particles, I wanted to start them off with some initial force. So I got their rigid body, I recomputed their mass from their protons and neutrons, set the rigid body accordingly. Then I regenerated some particles. I regret doing this as array lists now because I realized that I'm going to have to move things from one array list to another. It's going to be quite annoying. We'll see if I can pull it off. So start particles with some initial random force. Let's go rb dot add force. And how much do I want to add? Well, let's create a max range for it. Let's call it public const float max starting force. We'll call it 10,000 or something. And force needs to be a vector. So, can I get a random vector? No, I can't. I guess I could pick a random direction. Let's see what the internet has to say about this. Maybe there's a smart way to get a random vector. Nothing smart, apparently. So there is no built-in random vector. So I'll just make a cheap random vector using the 3 basic dimensions, x, y, and z. So it's going to be random dot range between 0 and max starting force for all 3 of the vector's components. Okay, so that gives me particles with some initial speed. Let's see what happens to my particles now. Boing, boing, boing. Look at them go, except for the ones that flew off into oblivion, but let's look at the few that didn't. Whee! Okay, now I accidentally gave them all positive force in one direction. I actually don't want to do that. I want them to be able to have negative force too. Well, rather force in the other direction. Negative is all relative. Alright, so now they should just kind of scatter off into different directions. Yep, there we go. And then some of them bounce and some of them don't. And it's all wonderful. And then they fly off into the ethereal eternal. And that's because I still haven't set up my outer sphere collider to do its thing. I just set it to a trigger. Okay. That's what that guy. I think I'm going to need a new script for this guy. Outer magnetic force operates differently because this is a trigger. I remember there being a limitation between objects that have a rigid body and how they behave with triggers, so we're going to see how this works. Now, rather than when it enters, objects are inside the sphere at all times, the trigger sphere. So we want these objects to get force when they exit the trigger. On trigger exit instead of enter. And then otherwise I think it's going to be pretty similar. I'm going to get rid of my debug statement here. I'm going to try to fetch the other's rigid body. And I want to still add force to it along its normal, but it looks like triggers don't necessarily... okay, so triggers have a collision rather than a collider. Unity get trigger collision point normal. Still want to find the normal along it. Maybe this isn't possible with triggers. Get the hit point in world space. Not helpful. The best I can do is add a bunch of explosive power, explosive force at that point. But that probably wouldn't work. Well, for now, let's just see if I can track the object and add any kind of force to it as we go. So I'm going to call it just some kind of vector. as a test. To verify that things with rigid bodies can strike trigger colliders. Okay. So I should get a bunch of these right away. And I didn't, which is bad news for me, because it means that they're not striking. Okay, let's try again. Let's say that each particle has a sphere, and it should be exiting the trigger at that point there. Ah, darn. So that doesn't quite work as intended. Okay, so let's look it up. Huh. I might be able to use on trigger stay to achieve the effect I want. Let's see if all of them are considered in the outer sphere in the first place. Ah, well, that's probably part of the issue, that they're not even considered inside of the sphere in the first place. Or perhaps I'm an idiot and I forgot to actually add the script to the game object. That would be a big help. Oh, that was stupid. Okay. Now let's see how it goes. Okay, so I do get a bunch of things hitting the outer sphere there. Okay, so now I need to be able to do this, basically, the to-do. I want to grab the particle's acceleration, or grab the particle's current velocity, and then accelerate it in the other direction. So I'm going to be getting a particle's velocity, get a game object's velocity as a vector. That was easy. Okay, so it's going to be rb dot velocity, and we want to accelerate it in the opposite direction of its velocity. Let me think how to do that. So if your velocity is taking you towards a point, you want to go away from the point. I guess I can direct you at the complete opposite direction. What if I add force proportional to the object's velocity? The opposite of the object's velocity times some multiplier. So that should direct it back towards the interior. It kind of worked for some of the particles, but then they quickly escaped. So I wasn't quite able to contain them. So you want to invert a game object's velocity. I can't use a physics material for this because I have a sphere rather than a bunch of containers. If this doesn't work out, I'll have to switch to a bunch of containers. Useless. Close enough. Nope. Well, I can get the magnitude and play with it that way. Let's see if I just boost the quantity of the reversed force significantly. Well, that definitely shoots them back towards the interior. The problem is that once they build up enough velocity, they'll be able to escape eventually. And they'll be able to escape by simply breaking the physics engine and clipping through the side of the sphere, which is kind of inevitable, honestly. There's really no way to get past that. The physics engine isn't perfect, so eventually things will clip through the side of the sphere and fly away forever. But these guys have been trapped in pretty well for a while now. So perhaps this is good enough. You just need to refresh the reactor with new blood every once in a while as it depletes its supply of particles in the interior. Well, they seem pretty stuck, so we'll roll with that for now. Okay, I'll do a... And then I'm going to recycle this for my regular collisions. So rather than deflecting it along the normal, I'm going to deflect its velocity in proportion to the magnet strength. See how that works. Wow, do they just get shot into space quickly. Alright. Turn that down a bit. Okay. They're getting bounced in there pretty good now. It's still not great. So ideally I could probably just use the physics engine's built-in bounce like it suggests too. Let's see what happens if I try to do that. If I give this a rigid body. And allow them to bounce off it the old-fashioned way. Well, they flew away relatively quick. Oh, I didn't save. Not bad, except that the material here isn't quite bouncy enough. Yeah, I preferred my old approach. I'm going to keep it reflecting on the normal. And that should be pretty good. And then we'll keep this tuned down, hopefully enough to keep it inside. Okay. I guess we can also cheat a little bit and make sure that items that escape just get yanked back into the Tokamak eventually. And I'm going to do that in the particle properties here. We'll do it in update, I guess. Yeah. Keep it locked within the reactor boundary that way. Let's say 400 is the furthest away it can be. And now what's actually inside the reactor? It's like between 0 and like negative 100, positive 100, and Z minus 100, Z 150. So let's go with there. So negative 100 to 100 on the X, 0 on the Y, and negative 100 to negative 150 on the Z. So basically, if a particle flies off into space in any direction, it'll just get yanked back into the reactor. Let's see if that worked. It did, although some particles are now moving really, really fast. It looks like they just keep getting yanked back in repeatedly. Whew, look at them go. Wow. Okay. So I think I'm going to add drag to my particles so that they just don't move faster and faster and faster until they accelerate into a million miles an hour, although I guess that's the point, isn't it? Okay, here we go. So the ones that strike the outer sphere end up getting deflected really, really quickly into super speed, whereas the ones that strike the interior barriers, they tend to be more conservatively speeded. So I think the problem is still with the way that I handle the outer barriers. I need to make the inner barriers stronger, and I need to make that outer sphere better. I gotta come up with something better than using the velocity of the thing against it. So first, let's try to use just the magnitude of the velocity, maybe. No, because that only gives me the direction. Let's normalize it to a magnitude of 1. So this gives me the direction of the velocity normalized to a magnitude of 1, and then I'll multiply by a consistent force, since if they leave the chamber, they're going to get yanked back in anyway. So that one left the chamber, that one left the chamber. Should see the outer sphere too. Okay, those are leaving the chamber too. a lot of particles leaving the chamber at any given point. So we still have a lot of particles escaping. Oh. So the opposite of your velocity normed times the outer magnetic force should bring you back towards the chamber, but I'm not really seeing the outer deflect very much. Actually, once they exit, they just sort of clear it pretty easily. Okay, new plan. So I'm going to flag particles that exit as outside the chamber. So I'm going to create a new field, public, call it boolean is outside chamber equals false for all particles at the start. It's a bool. Yes, is outside chamber. And then as long as you are outside the chamber, I am going to continue to apply force back towards the interior of the chamber. So we're going to have the center of this thing be the origin of the world, which is 0, 0, 0, which I think is true. But let's call it public vector 3 chamber center equals new vector 3. The center of the world is at 0, 0, 0, and I think that it always will be for my purposes. So when you exit the chamber, oh, no block commented. C#, the block comment is so annoying, I never remember it. Control-Shift-U or something. We're going to try to pick up the particle properties of the other object. We're going to set the fact that it's exited the chamber to true. We're going to do the same thing in reverse when you re-enter the chamber. Guess I should do a null check there, just in case we want anything else to collide down the road. Okay. Error because I haven't saved this yet. Alright, I'm also going to set it to outside the chamber here. And in the physics frames, so in fixed update, or in update, it doesn't matter. So the difference between fixed update and update, if you're working on a real-time Unity app, is that fixed update happens a fixed number of times in a given frame rate. So fixed update is usually better for physics computations, whereas update runs as fast as possible. So if you want something to happen kind of as fast as possible, like let's say you do a force thing in update, right? If the user's computer is a little slower, then they're not going to get as much force than the user's computer that manages to generate more frames. So you very rarely want physics stuff to be proportional to the frame rate. But in this case, I actually kind of do want to apply the force as fast as possible, now that I think about it. So I want to, I think I already have the rigid body. as a global here? I do. So I want to add force towards the center. That's going to be transform.position minus chamber center. That gives me the vector between them, I think. Something like that. So if is outside chamber, I want to apply force towards the chamber center. Vector towards point. I might have to normalize it. Let's see. You're getting hurled off into space, which usually means that you did it the opposite way. Let's see. Oh, okay, cool. They're getting smacked back into the middle as soon as they exit, which was the intent. They get a considerable amount of smacking. Nice. I'm still a little bit disappointed in the quantity of bounce that we get. It's still not exactly proportional to how fast they were going. I'd still like to do a better bounce factor off the internal magnets. Here we're looking at a decent idea, but basically the same thing that I'm doing. Adding force along the normal. Which will usually do fine, it's just that these items already have a lot of force to them, so... Yeah, still looking at normals. Well, a physics material could do the job, but I don't know if I really want to do that. Let's try. I haven't used physics materials very much, so I can't say a ton about how this works. I think you have to add... You add physics materials. Ah, it has to be applied to the colliders. Ah, there we go. Okay. So I guess I'm going to need a new physics material. I'll put it in my prefabs. Bouncy. Okay. How bouncy is the surface? Value of 1 will bounce without any loss of energy, so I want it to gain energy when it bounces. So let's call it 1.5. Ah, you can't add a bounce of more than 1. That's going to be a problem. We'll see if this works for my barrier colliders. Maybe this makes them bouncier. Well, it certainly looks bouncier. Everything's definitely accelerating. So yeah, I think that worked. So I've got my bounce, and then it also adds force along the normal, which simulates that extra oomph that I need to get them going faster and faster. So I think that they're bouncing off of each other now, so that's good. Okay, next order of business is that particles are supposed to repel each other until they're moving so fast that they overwhelm their natural inclination to repel one another. So I'm going to add that. That's going to be probably part of particle, but I might separate it out later. So we'll call this nuclear force. I think it's called the weak nuclear force. Yeah, I guess let's call it that. Weak nuclear force. I have to add a script for this. And weak nuclear force is going to require another collider. So this object now has a ton of colliders attached to it. For that, I'm going to do a sphere. And we're going to make it large, something like that big. So much bigger than the actual particle itself. Will be the influence of its nuclear force. And then the closer you get to the particle, the stronger it becomes. So it has to apply to all of the objects that are inside of it. I think I can pull this off with on-trigger stay without having to develop a array list or anything. So let's see. On-trigger stay. What does that do? Once per frame for every collider other that is touching the trigger. So that should work. Rigid body RB equals other dot game object get component rigid body. Okay. And then again, we want to apply force away from this particle. So we want to apply force in a normalized direction. I should probably make a constant for this before I forget. $5,000. This thing 5,000, and I should use my reactor bounds variable instead of just having magical 400s in there. And I should probably put this in fixed update because that's the right thing to do, and I don't want to get you guys the impression that you should be doing physics in the update method. If this is for demonstrative purposes, you should probably do that, so that's the right thing to do. Alright. Oof, look at that particle rumble and roar. Okay, so the weak nuclear force is a trigger, and on trigger enter, it's going to look for the other rigid bodies that are attached to it. If RB is not null, it's going to propel them away from this object. So RB dot add force. The distance between the 2 points again. So it's between this game object and other dot transform dot position, normalize those, and then multiply by some proportion to the distance between them. Some proportion to the distance between them. So multiply by, we'll do vector 3 dot distance. You know, I don't really need distance if I've already got the distance between them that way. So yeah, that vector already represents the distance. If it's the vector between the two of them, then that's the line between their two positions. Okay, so every particle will reflect other particles that run into it. Alright, let's try. Gonna have to add some more particles back and then move them around a little. Okay, here we go. Do they repel each other? I think they do. They certainly don't touch. These spheres never seem to touch. The outer spheres of any two particles never seem to touch. So that's a good start. And if I wanted the nuclear fusion element of this to work, I would need something to detect when they've actually collided with a particle. So I made layers last time. I made a layer for the reactor barriers. Let's make a layer for particles. And let's try adding all the particles to the particle layer, including the children. The weak nuclear force will be part of the particle layer too. I think all the collisions and everything still work with that in place. Cool. And now when the particles collide, something is supposed to happen. There's supposed to be a nuclear fusion. So I'm going to try to mess around with that on the particle properties method. Okay, so let's add a on collision enter. If collision dot, how do you get the other game object? Compare its layer. So I want to compare it against particles. Then a fusion has occurred. Okay, and in order to rig this to be more possible, I'm going to weaken the weak nuclear force significantly so that they don't repel each other as much. Yeah. Okay. Well, they're certainly not fusing. Oh, I got a couple. I got a couple fusions, but it looks like I got them way at the start. And then never again. I think everything kind of got stuck after that. Oof. That's an unfortunate bounce pattern. Looks like things can occasionally get trapped, bouncing around like that. Well, once there's other particles in place, I'll just knock them out of it. Okay, well, with that in mind, let's start firing up the reactor. I'm going to add my particle to my prefabs. And then let's make a particle spawner. Particle spawner. Combined with the script. Particle spawner. Okay, particle spawner is going to get a button. We're going to give it a UI elements, a button. It's going to add a bunch of other stuff. In addition to that, we're going to make it relative to world space. Yes, screen space, world. That way it doesn't have to be a parent of the camera. And we're going to anchor it to the bottom left-hand corner. And we're going to call it more particles. This is going to just shove particles into the reactor. Okay, so my particle spawner takes this button. I want to take a spawn location. Do I want to spawn them all in one place? That seems kind of silly. I guess I want to spawn them all along the Tokamak somewhere. So I guess I can call it spawn range. I don't know what happens if they spawn inside the middle. Probably just evict them because it's a collider, but we'll figure it out. And distance particles spawn from origin. Okay, if you leave a tooltip like that, it pops up when you hover over it in Unity. Really helpful. I think 150 is the biggest I want it to be. Public game object particle. Yeah, just do particle. And when the particles are created, do they automatically spawn all their stuff? Yes, they regenerate them right at the beginning. And then they recompute mass right at the beginning. I'm going to change this process slightly so that we're not recomputing mass and everything every time a particle is created, and then when we update it. So we're going to regenerate them and recompute their mass, not on start, but at a specific point. And then anytime, I'll just do it once at the beginning. Okay. So that's particle prefab. Now I want a button click. keep forgetting those uppercase letters. Void spawn particles. Let's make a void const int particles to spawn. See if 100 is doable. And then we're going to instantiate them. Okay, first we need the vector, which is going to be a range within the spawn range. So it could be anywhere inside of the reactor. Then we'll need a quaternion. I'll spawn an identity for convenience's sake. You've seen me use that a lot for rotation. Rotation is complicated. So I tend to avoid having to do customized rotations when possible. Okay. Oh, forgot the name. So particle prefab, this Tokamak here, this Tokamak there. Okay, p dot I need the particles property of this. Particle properties equals p dot get component particle properties. We'll call it properties. So you can either have one hydrogen deuterium or sorry, one neutron deuterium or two neutron tritium. So properties dot protons is 1, right? That's how we do this. Properties dot neutrons is random dot range. It could be, oh, it can't be 0. We don't feed zeros in, so we only do 1s or 2s, I think. And then we want to recompute everything. Okay, and we want to do this that many times. Seems good. Just have to drag the prefab in to link it. Alright, so more. Looks like we have a problem with the mass. No big deal there. That doesn't happen too often, so I can spare another get component call there. Wow, that's a lot of particles. Look at them all go. I forgot the y-axis is more limited. They could only be between 50 and 50. So let me mess around with that first. So I guess I could just always put them at 0. They always just get inserted on the axial plane of the other two doohickeys. Yeah, cool. Where are they at? Where are my particles? Have to hit the button, don't I? Yep, there they are. Look at all those particles. And hey, they are hitting each other occasionally, but not that often. So fusion's happening, and then some other stuff is supposed to happen when fusion happens. But let's get to the real cool part here. Let's go ahead and build this to the phone and see what the phone can handle. That was the whole point of this exercise for this class anyway. Before I do that though, I want to make sure you can actually see them in the camera, because I don't really think you can see the particles. Well, you kind of can, but they're very, very small. I guess once you get up to like 600 of them, then you can definitely see them. I don't want to crash Unity, so I'm going to pause that. Alright then, let's go ahead and do it. Let's see what you can see on the phone. This is Tokamak V1. Okay. I'll just ignore that because that's from me being lazy and recycling the tools from the Android version. I guess let's take a survey, see if anyone's still awake. Made with Unity. Wow, a lot of people are really giving this phone some credit. The more particles button is teeny. Alright, that's fine. Here we go. I can't tell if I've clicked it or not. It's very small. Okay, there's definitely some. I think that was one press. 2, 3, 4, 5, 6, 7, 8, 9. Uh-oh. It's really slowing down. But that was just an instantiation, so that's 900. Okay, next push makes it 1,000. Ooh, 1,000 really crawled, but it recovered after that instantiation. So instantiation is still really inefficient here. Like I said, that's usually where you see those stutters the most, is during instantiation. Oh, I can actually click it here instead of doing it on my phone. That's easier. Okay, so that's 1,000 particles. It's getting a little choppy. 1,100. Let's see if it recovers. It looks like it's going to stay choppy at 1,100. Yeah, it's still choppy. It's not recovering from instantiation this time. And, you know, it's getting a little hot, but it's not too crazy. So it's probably bound to a single CPU core on the phone. Add some more. Let's see how many it takes for it to crash completely. So it took about 1,000 for it to get choppy. So I think the people who answered B, which was nobody, got the closest. But the C people, I give it to you too, because we just barely cleared 1,000 before it started to stutter. Well, it hasn't crashed yet, but it's very stuttery now. Which is fine, as a physics simulation goes. It doesn't have to run in real time. It's obviously not running in real time. Particles don't move that fast. They move about 1 trillion times faster than that. Just keep clicking, just keep clicking. What does Android do when it runs out of resources? Uh-oh. Nothing's moving anymore. It's still registering touches, though. So Android basically keeps the system going. It doesn't hard fault like some of our desktop environments do when it runs out of resources. It tends to fail in other ways, but it usually doesn't just die completely on the entire system level when it runs out. So that's something that's really great to Android's credit. I mean, we're probably close to 3 or 4,000 at this point, and it can still do the occasional frame, but we're looking at less than 1 frame per second now, obviously. I think, again, the biggest mistake that I made was doing all of the, like, it instantiates a proton, a neutron, potentially another neutron, every time a particle is instantiated. So every instantiation call for a particle spawns 3 more instantiation calls for its subcomponents. That was inefficient. I should have just made a different particle prefab for each kind of particle with them already pre-instantiated. And then using that array list was also probably a bad idea. I think that probably cost me a lot of overhead on the particle creation. So even if you think about this stuff in advance, sometimes you'll run into a lot of issues. Okay, well that's about all the phone can handle. It looks like it's not going to crash, but it's also not going to render frames anymore. If I open and close the application. Hey, look, it picked back up. All right. Well, I've got another 10 minutes left, and that was really as far as I wanted to go in it, so I guess I'll just do a couple more fun improvements. I'm gonna do... Let's get rid of the skybox and just make it solid black in the background or something. Solid something. Solid one color. White's too bright. Gray's too gray. Red's too red. Purple. Sure, purple it is. Alright. And play with the barriers a little bit, because sometimes it looks like they're kind of flying out, which I don't like, so maybe make the outer sphere smaller so it starts kicking up that force sooner. The force that redirects you back inside the sphere. That takes effect sooner. I don't really like how the barrier boxes can be broken out of too, so maybe move those up a notch so that they're kind of hugging the inside of the reactor there. The inner sphere I think was perfect, so let's try that out. Yeah, that looks much more representative of them bouncing around in the interior. So that's lovely. Let's see if we can follow a particle through its journey. No, they move too damn fast. Eventually they just end up bouncing up and down, it looks like. Once there's enough of them, they just get sort of stuck in this environment where they bounce up and down until you add more. So not exactly realistic. I think that has to do a lot with the nuclear force element to it, repelling all the forces around. Lots of fusion happening here. You know, look at all those fusion prints to console. That's a lot. But yeah, they just they end up getting into a steady state where they bounce up and down forever. So that's amusing. I guess one way I can do that is to add a little bit more horizontal velocity to them, or maybe just engage them with more velocity randomly. I'm sure this isn't actually how it works. A few still manage to escape once in a while, and then they get yanked back in. A little bit of a bug. You can actually get yanked into the outer sphere area only and not be contained inside the Tokamak, and then you're trapped out there because you keep smacking the top barrier of the reactor. Okay, let's see how many my computer can handle. Hopefully Unity doesn't crash as we go. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Give it a second to adjust. Doesn't look like it's going to be adjusting. Looks like that's it for good performance. 21, 22, 23, 24, 25, 26. So a phone's not really that weak, you know. If a strong desktop can only handle 2000 or whatever, you know, in the high twos maybe, then the phone didn't fare that much worse. Whew, I was able to get out of there without crashing. Awesome. So don't underestimate the phone, but also be aware that it's not obviously unlimited in its power. So what happens when fusion occurs? I guess I can try to figure it out. The other particle is supposed to lose a neutron to this guy, and then one of them lose a proton and a neutron to this guy, and then the neutron flies away on its own. But I think only deuterium and tritium fuse. Well, too complicated for the last 5 minutes anyway. Maybe I would output how much energy they pumped out or something like that. Maybe I would output how much energy they take in or something like that. It's some more additions here to make, but I'm pretty satisfied with this as a Tokamak reaction simulator, so I think I'm going to stop there. And I'm going to hop into Discord to see if anybody has some last minute questions for the upcoming checkpoint on Thursday. Make sure you turn something into Canvas so I can evaluate it, but more importantly, make sure you have something to show me when I meet with you. So expect about 5-10 minutes each, since there's only about 10 of you. Okay, see you Thursday.